Hey, feeling good, like I should. When in dark, walk around the neighborhood. Feeling blessed.
Alrighty, let's take a look at the different situations with linear and exponential growth. We learned that in yesterday's lesson that compound interest formula involved an exponent, and so the graph that is associated with that type of growth would be considered an exponential growth graph, as opposed to the linear graphs, which were the straight lines that we've been spending so much time on. So let's get to it. First of all, let's just remind ourselves linear growth involves a constant growth rate and a straight line, while exponential growth is not a constant growth rate. The growth either increases or decreases over time, and the graph is going to be curved. So patterns in tables, graphs, and expressions give clues about the kind of growth that's being represented. Today, you will work to identify whether a table, graph, or situation represents simple interest or compound interest based on the kind of growth that you see and that is shown. You will also compare the different kinds of interest in situations to see which one is the better deal. By the end of this lesson, you should be able to answer these questions. What are the patterns in the tables, graphs, and expressions for each kind of interest, and what are the differences between the two kinds of interest, and how does the pattern relate to how the amounts are growing? All right, here we go. John needs to borrow $250. I'm going to highlight that. Moneybags Municipal will charge him 8% simple interest each week to borrow money. Okay, so it's weekly at 8% simple, and the principal was $250. So if I were to use the 5B process and record all this, the principal is $250, the interest rate is 8%, which is 800ths in decimal form, and the amount of time will be some unspecified number of weeks. So if we're going to calculate the simple interest for this situation, we're going to use the formula I equals PRT. And that would be taking $250 times the 8% to give us an amount of $20 per week is the amount of money that he would earn in simple interest from Moneybags Municipal. Now let's take a look at the other situation. Scrooge Savings will charge him 6%. I use this one. I'll just use this one. 6%. Once again, it's compounded, but it's per week. So in this situation, let's analyze what we got going on here. We've got Scrooge Savings, where the principal is the same, $250. You've got a 6% interest rate instead of 8%. So the interest rate is lower. However, it is weekly and it's being compounded. So we're going to use the formula A is equal to P times 1 plus R raised to the T power. And remember what this formula means. The amount of principal is going to grow according to this particular multiplier. The multiplier is 1 plus the interest rate, which is 100% of the principal plus the additional interest rate. So it's going to be 1.06 over unspecified amount of time. So the principal, and then this gets repeatedly multiplied every single week. So T will be the number of weeks. Okay. So we've got our two different situations here. And what we're going to do is this. We're going to go to a table and create two different tables, one for Moneybags and one for Scrooge Savings. And it says, show the amount John owes after each week for 12 weeks. Okay, so we're going to come over here, and I'm going to pause, and you should pause, but I would label these, copy this down exactly how you see it. Now, you'll notice I did not go all the way up to 12 weeks per week. It gets a little tedious after a while. So I did the first 4 weeks, then the 10th week, then the 12th week. You do the same thing. I think this will be easier. We'll get all the information we need for our graphing, if we just find these dollar amounts. Now remember, money bags is a simple interest situation, so I equals PRT applies, and we've already figured out 8% of 250 is $20, which means that John will be making, is that his name, John? Yes, John will be making $20 every week, and then figure out what the new amount is. This one's going to take a little bit more time. If you don't have your calculator, this is a nightmare. So use the Google Scientific Calculator with your Chromebook or computer, or hopefully you've got a calculator to do this that allows you to raise this to a certain power, right? You want to be able to raise it to the 10th or the 12th power to find these amounts. So go ahead and work through that process. In fact, I'll get you started with the first two on each one of them, and then pause it and you can fill in the rest. So starting with money bags. Simple interest. In 1 week, that would be $20, which means that the new balance would be $270. In 2 weeks, that would be 2 times 20 would be $40 earned, which would be $290 as his new balance. That's easy. This one, a little bit trickier. So I'm going to grab my calculator, clear this out from the work we did in the previous lesson, and let's see. All right. This is the formula. And in 1 week, that would be 1.06 raised to the first power, and it's just going to stay the same, right? Then multiply that times $250, and that dollar amount is $265. So that means we're going to have to kind of do this in reverse. Do I have this on blue? I think I do. Yes, $265 is the new amount, which means you must have made $15 that first week, right? Because I'm taking this, subtract the original amount, to find the amount that I've earned up to that point. Okay. So notice week 1, the simple interest actually paid more than the compound interest. But that's because this is 8% and that's 6%. Generally, we think that the compound interest is eventually going to make more money, and I think it will. Even though this is 6% and that's 8%, it'll take a little time, but eventually this is going to pass that. Question is, when is it going to pass? That'll be interesting. All right, so now let's do the second one. Let's take $250. No, what are we doing here? We're taking 1.06, and now we're going to raise it to the second power, and that's going to be 1.1236. Multiply that times the original amount of 250, and that's $280.90. So that means you must have made $30.90 after 2 weeks. Okay, no. This isn't making. This is a loan, right? Yeah, he wants to borrow. Ouch. Ouch. That's a lot of money you got to pay back. Weekly 6%? Forget about it. Okay, whatever. All right, you can do the rest. I've now shown you how to do this twice. This should be relatively simple. Just take a little bit more time with your calculator. When I unpause, I'll have all the answers for you to see. Okay, so make sure you're pausing so you don't accidentally cheat off of me. Alrighty, let's take a look at what we got here. You see that money bags is increasing by $20 per week, and so after 12 weeks, money bags would be charging you an additional $240 on top of what you borrowed. You have to pay back what you borrowed plus give them the interest. So you owe them $490 at the end of 12 weeks. With the Scrooge savings, what you got going on here is a lower interest rate. And so you can see even after 10 weeks, Scrooge savings only charging 6% was still a better deal than money bags because of the money bags charging 8%. But it's between the 10th, 11th, and 12th weeks. I think it's around the 11th week where it finally starts to change. And the compound interest, the fact that you're not only applying the interest to the original principal, but all of the accrued interest earned to that point, where it starts to build beyond what you're getting charged at money bag. So it's in the 12th week here where you would actually owe $503.05, which is more than double what you borrowed, whereas here you're paying back only $490. So let's see what that would look like on a graph. So I would like for you to take your table. Your independent variable is your time, the number of weeks. That's going to go on your x-axis. Did I forget to label my x here? Let me label my x here. Okay. And your dependent variable is the amount of money earned. Okay, so your new dollar amounts. So go ahead, let's plot these points on a coordinate grid. I'm going to pause it again, and I would like for you to create this coordinate grid, and then we'll see how the two graphs, they compare to each other. Okay, one of them, simple interest, should form a straight line because it's constant growth. The other should have a curved line because it's exponential growth. Okay, so go ahead and pause and plot those points. Don't bother labeling them. Just plot them like we did with the scatter plots, and we'll see how those graphs end up looking. Alrighty, here we go. This is the graph. So we're starting off, we're graphing 0. That's our y-intercept for this situation. It starts at 250. In fact, both of them start at 250. But you see that let me go ahead and use a red line here. You see that the simple growth, or the simple interest, forms a straight line, right? That is what we expect from a constant growth type of equation. But actually I could have kept it on there. Hold on for a second, let me bring this back. But you'll note, well, I guess you can see it right there. You see how the blue starts at the same, but it is, because it's a lower interest rate, starts out lower, but eventually gets to that point where the curve eventually is going to intersect somewhere in here between the 10th and the 12th week. Yeah, that's what we set up here. So Screwed savings being exponential growth shows a curve compared to a straight line for the linear growth of the simple interest problem. So what did, I think we had some questions that we still had to address over here. Said, which bank will charge him more if he pays the loan back in 12 weeks? Well, in 12 weeks, the compound interest is going to charge more. And so it's $503 versus $490, so that's $13.05 more by going with Scrooge savings if he's going to take 12 weeks to pay it back. But if he's only going to take 4 weeks to pay it back, remember that 8% interest rates made money bags a little bit more expensive at the beginning, $330 after 4 weeks compared to $315.62. So if he was going to only do it for 4 weeks, then he should choose Scrooge savings over money bags. Right, so the table at the right represents the balance of Devin's bank account for the last 5 months. Notice the time is in months, and the balance is shown at the right. Has Devin been earning simple interest or compound interest? Okay, so there's one easy way to find out. Let's figure out what is the difference. How much did this grow by here and here and here? If it's growing by the same amount, it is simple interest. If the amount is growing over time, that implies exponential growth, and it would be compound interest. So I'm going to take $263.25, 263.25, and I'm going to subtract away 257.5, and that gives, stop, 263.25 minus 257.5. Okay, $5.75. So I'm going to add this to 263.25 and see if I get 269. 263.25, and indeed I do. So when I add 575 to that, plus 5.75, that gives me, stop it, 269 plus 5.75 is yes. Okay, I feel confident. We are adding the same amount each time, so this is simple interest. The amount is growing by $5.75 per month, which is a constant growth rate. All right, now for the last of this lesson. If Ari borrowed money from her uncle to buy a new bicycle, she made the graph at the right to show how much interest she will need to pay if she pays back the loan at different points in time. About how much interest will Amari owe her uncle if she pays him back in 3 months? So this red dot is 3 months, and what would you say that dollar amount appears to be right around there? Maybe about $16. And the second part, when will she owe him $40? So 40, that looks like it's a little bit beyond the 6 month time period. So is Amari's uncle charging simple or compound interest? How do you know just by looking at the graph? Well, is it a straight line or does it appear to be a curved line? Well, let's check. It's definitely a curved line. It is not straight. So with that, because it's a curve, we know it is exponential growth, not constant growth. So that is a compound interest type of problem. All right. So how much time do we have? Do we have time? We have time. All right. I'm going to teach you something here. I'm going to teach you something that is called the rule of 72. And this applies to all situations that involve compound interest. This is sort of a mental process that bankers and finance people will use to determine how long it'll take for an investment to double. Okay, so hold on for a second. Let me write down some amounts in here. I'll be right back. All right. So we're going to take a hypothetical $1,000 investment. You make up any number you want. The number, trust me, makes no difference. This could be $1 million. It could be $500,000. It could be 25 cents. Doesn't make any difference what the dollar amount is. It has everything to do with the rule of 72. I don't know why this rule works. I would love to understand the deeper mathematics involved here. I'll admit I've never looked into it, but I don't think I really care to. It's not something that I would be teaching you other than trust that it works, and I'll prove it to you with the calculator. So the rule of 72 works like this. If you take, I'll do this and now I'll do it in green because it's money we're talking about here. Okay, so if you take an investment, it's going to double. If it's at 1%, it's going to take 72 years for that investment to double. So if you saved $1,000 in a savings account that paid you 1% using compound interest, in 72 years, it will be worth $2,000. 1% is a horrible interest rate. Just saying. If you put it into an account that pays you 2%, it'll take 36 years before it doubles. 3% will pay you in 24 years, it will double. 4% will take 18 years before it doubles. I'm going to skip the 5 for a second. 6 is going to take 12 years before it doubles. And now if I show you these next two, actually the next 3, you might figure out what the pattern is if you don't already know what the pattern is. It's going to take 9 years for an investment to double if it makes 8%, and it'll take 8 years if it earns 9%. And in 10 years, oh, stop that. I'm sorry, not in 10 years, at 10%, it would take 7.2 years for this investment to double. Now, are you seeing the connections here? What do you notice about this number here and that number there, this and that, this and that? If you're noticing that the interest rate, whatever you multiply times the interest rate to give you 72 for an answer, that's the number of years it will take for you to earn that money, okay? So that means to figure out what 12 is, 12 times 6 is 72. So if you happen to be lucky enough to invest in any kind of a mutual fund or any other investment opportunity that pays you 12%, your money would double in 6 years, okay? In 5 years, how do I figure out what would it be in 5 years? Well, I'm just going to take 72 and divide it by 5, and that is 14.4. So 14.4 years, I think I might have reworded or worded something wrong there. At 5% interest, it'll take 14.4 years for that investment to double. So let's prove it. Let's take and use, I guess this would be the, this would be the formula here that we're going to use. I'll do it in red so it stands out. The new amount which in this case is going to be $2,000 or something really close to it, right? This is an estimate. Is going to be our $1,000 that we invest plus 1 plus R over the given number of years, right? So what we're going to do is, I don't want to put that A there, that bugs me. Okay, so the new amount is the 2,000. So let's go ahead and pull our calculator and let's see if we do this. Hold on for a second. Management. All right. I got things figured out here. Come on. Okay, there we go. All right. So I'm going to take this amount and I'm going to apply one of these percents to it. And then I'm going to raise it to this power, because that would be the number of years. And we'll see if the answer doesn't become 2,000 in almost all of these situations. Let's start with 3%. So this is going to be 1.03, since 3% would be 300, right? Plus the 1. Now we're going to raise that to the power. No. 1.03 raised to the power. We think it's going to take 24 years. So I'm going to go 24. That's going to give me that as my multiplier. And you notice how it's a little bit more than 2? That means that we're going to multiply that times 1,000 and it will double, right? It ends up being $2,032.79. Okay, but we're talking approximately. Somewhere as you get really close to 24 years, your initial investment becomes over $2,000 or right about $2,000. To try this again, let's go to 8%. We think it's going to take 9 years. So we're going to take 1.08, raise that to the power of 9. That is almost 2, isn't it? Now we multiply that times 1,000. And it's a little bit short, but once again, we're estimating. It's just around the corner before that becomes $2,000. Okay, now let's try the 10%, see if we can do an exponent to the 7.2. I don't think I've done this. 1.1, that's 10%, raised to the power of 7.2. Does that get us really close to 2? Yes, it does, times 1,000. No, that's 10,000. 1,000? Okay. So once again, these are estimates. But a lot of times that's what we're going to do, is we're just going to do an estimate and then use the calculator to get the exact amount. But this is what we call the rule of 72. It comes in handy. So if I give you a problem on the test that says, okay, you've got a $24,000 investment and it's at 4%, how long will it take before that money doubles? You will know it'll take 18 years because of this table right here. 4% will double its value in 18 years and it'll become worth $48,000. All right, so that's the rule of 72. That concludes our lessons on compound interest. And from this point on until the end of the chapter, we're pretty much going to have compound interest showing up in examples in our homework. So make sure you get that homework complete and show all of your work. And luckily with compound interest, most of the work is done with the calculator. So it's just a matter of writing down the formula and plugging the numbers in and then showing me what your answer is. Not too much trouble. All right, take care. Bye.
Hey, feeling good, like I should. When in dark,